Okay, so let us continue our discussion on reactor stability analysis. We discussed the steady state solution for concentration profile, and then we got a complex expression for steady state profile for temperature. So, the equations were like this, and when we solved for steady state temperature, what we got was an expression of this form, minus delta H upon rho C p k 0 e to the power minus E A upon R T steady state F C F upon V divided by F by V plus k 0 e to the power minus E by. So, we are using the notation E. So, let me get rid of this A here, E upon R T S, right, and this was equal to F upon V plus U A upon V rho C p times T steady state plus in fact minus F T feed T feed upon V plus U A T jacket upon V rho C p. So, this was the expression that we had in front of us, and then we said that in order to determine the steady state temperature, we need to individually draw say the graphs of the left hand side and the right hand side, and the point of intersection would be the steady state temperature. Let us see what kind of functions are these. Let us first look at the left hand the right hand side. Now, f by v is a constant, so f is a constant, v is a constant, u a rho c p, all of these are constants, right. So, let me say that f upon v plus u a upon v rho c p, let me call it as some constant p. Okay. Further, feed everything is the system is assumed to be at steady state. So, feed rate would be constant, temperature of the feed would be constant, the material properties have been assumed to be constant. So, u a v rho c p everything would be a constant. So, therefore, I can write f T f upon v plus u a T j upon v rho c p. Let me call this as another constant q. Okay. So, therefore, in light of this, the right hand side would be what? P times T steady state minus q. And what kind of a function is this? This is simply a linear function with p and q's as constants. Okay. So, not very difficult to see that you would have simple and what kind of quantities would p and q be? F, V, U, A, rho, C, P are all positive. So, P would be positive. Similarly, F, T, F, V, U, A, T, J, rho, V, C, P are all positive. So, therefore, P as well as Q would be positive. So, P, Q greater than 0. Let me plot this and write the nature, see the nature. So, f of x is equal to p x minus q. Okay. Well, not very difficult to see how this plot would look like, and we would also set p and q between 0 and 5 to confirm that they are positive, 0 and 5. Fine. Now, what about the other quantity? Delta H. So, the left hand side now, minus delta H K 0 F C F upon rho C P V. Let me call this A. Okay. Let me call E upon R as B. Let me call F by V as C, and let me call K 0 as D. So, this will make the left hand side what? A e to the power minus b upon t steady state divided by c plus d e to the power minus b upon t steady state. Okay. So, a e to the power minus b upon t steady state plus c upon c plus d e to the power minus b upon t steady state. So, let me try to plot this function now. G of x is equal to a e to the power minus b upon x divided by c plus d e to the power minus b upon x. Okay. Now, let us also analyze what kind of quantities these are. So, B is E upon R. So, B is certainly greater than 0. F by V is C. So, C is certainly greater than 0. Pre-exponential factor is certainly greater than 0. Now, rest all the quantities in A, so K 0, F, C F, rho, C P, V are positives, but delta H depending upon exothermic or endothermic may be positive or negative. Okay. So, let us for sure set B as positive, C as positive and D as positive. Okay. Now, I see that the intersection of the two curves. So, the intersection of left hand side, which is given as a e to the power minus b upon t s upon c plus d e to the power minus b by t s, and a straight line given as right hand side is equal to p t s minus q should give me the steady state. Let us see if this is correct. So, let me do one thing. This is f and this is T s. Okay. In case of f or g, in fact. Okay. So, let me look into this. Let me zoom in. I will be interested only in the first quadrant, but let me zoom in, so that I will be able to have a look into this better. Okay. So, now what I see is that I have the left hand side involving exponential. So, you have this nonlinear curve, I have the right hand side which is a straight line, you get this, and then you get one point of intersection, and therefore, this is your T steady state. So, you fix the flow rate, you fix the feed concentration, you fix the jacket flow rate, you fix the jacket temperature, you get one steady state. Looks very simple, very trivial in fact, right. But let me now do a small arrangement with the parameters of the system, okay. And let me then see if I see something very different and in fact something very interesting. So, let me try to change the parameters, and what I will do is I will change the value of P and Q. Let us see what I have done. So, I will zoom in further, and now what I see is that instead of one intersection which you would expect to be a unique solution for your system as the steady state temperature, now you have 3 points of intersection. Okay. So, what are the 3 points of intersection? Point 1, point 2, point 3. The absolute values do not have any significance here, because you will punch in various values of heat transfer coefficient, flow rates, etc. What I want to show you here is that you in fact have 3 steady state temperatures. Now, the question is, how can you have 3 steady state temperatures for the same state of your system, same flow rate, same temperature, feed temperature, same jacket temperature and so on? Well, because the system is non-linear. Okay. So, since the system is non-linear, now you have the intersection of your heat generation curve, which is a non-linear curve, with your heat removal curve, which is a straight line, right. So, we would be interested in knowing the natures of these solutions. So, let us clearly point out that you have 1, 2 and 3. So, there in fact can be 3, in fact there can be 3 intersection points corresponding to 3 solutions, there can be 2, there can be 1. Okay. So, now if I draw the general trend of this equation here, what I see is this. So, this is steady state temperature, this is function f of steady state, g of steady state. One of them is a straight line, I know, but the other one look like this. In one case you had one intersection point which is like this, and therefore, you have a unique steady state. And what is the importance of this unique steady state? T steady state 1. The importance of this unique steady state is that Well, it makes your life easy, because you know that I have set my feed temperature, I have set my feed concentration, I have set my temperature of the jacket. So, I will calculate and I can know what would be my reaction mixture temperature, steady state reaction mixture temperature, very simple. Now, I have a case where you have 3 intersection points, 1, 2 and 3. So, T steady state 2, T steady state 3 and T steady state 4. So, for the same input flow rate, for the same flow rate of jacket fluid, for the same flow rate of for the same temperature of jacket fluid, for the same feed concentration, for the same feed temperature and all the material properties, now you have 3 steady state solutions, and then therefore, it becomes imperative to know that if I am going to give the same values of the parameter, where am I going to land up? Because previously we saw that the variation of the concentration with steady state temperature. So, this is the steady state temperature, this is the steady state concentration, look like this, right. So, therefore, when you want to know the steady state concentration, you would like to know the steady state temperature. But now, instead of one temperature, I have 3 temperatures, and therefore, I must know how much is the output which I am going to get from my system. Now, there is an ambiguity. Okay. So, what we will need to do is we will need to analyze the stability of these points. Okay. Before we do that, what we also need to do is this, that if you have, well, you got this curve by an intersection of the f function, which was nothing but the heat removal, g function, which was nothing but heat generation, and you try to determine the intersection. If you rearrange these equations, you can as well draw several other graphs. Okay. For one of the graphs, for example, would be this. T jacket, so T jacket here versus T steady state here. Okay. In general, what would you expect? Well, if I set some flow rate of the fluid in the jacket, and that jacket flow rate jacket fluid has some temperature, then because of the heat exchange at steady state, I must get one unique value of the steady state temperature, okay, inside the reactor. So, what you should expect is that as my jacket temperature goes on increasing, my steady state temperature should go on increasing, some kind of a pattern like this. So, you get for a jacket temperature, you get a unique steady state temperature, but that does not happen. In fact, the way we plotted the previous plot, if you rearrange everything as a function of steady state temperature on one side and jacket on the other side, what you will get is, what you will observe is that you in fact get a curve which looks like this. So, let me draw the curve which which you will get from a similar analysis. I am leaving the analysis for you, I am leaving the rearrangements for you to do the nature of the curve, and if you put that in Desmos, you will get this kind of a curve. The curve looks like this. It is an S shaped curve. Okay. It is an S shaped curve. So, now what is the problem with this curve? you would be operating your system at certain jacket temperature. So, let me draw 3 vertical lines. Okay. So, these are the operational lines. So, if I drop the first vertical line here, I get this intersection, which means that for this jacket temperature T jacket 1, I will get this steady state temperature T steady state 1. Okay. Similarly, I drop this another operational vertical line for T jacket 2, I get this steady state temperature, again not a problem, T steady state 2, one jacket temperature, one steady state temperature, that is fine. Now, let us have a look into this T jacket 3. For T jacket 3, you have T steady state 3 1, T steady state 3 2, and also T steady state 3 3. You have 3 steady state temperatures. Okay. But we have previously seen that it's possible that you get multiple solutions, but all of them may not be stable. So, if you have one particular solution which is unstable, then you would not physically observe that solution, and therefore, it is okay, you need to worry about only the stable solutions. How would you get an idea whether a solution is stable or unstable in all of these cases? Well, what you will do is you will linearize your system. Okay. So, how would you linearize your system? I will assign this as a function f, or f1 rather. I will assign this as function f2. Okay. So, this is an exercise which I am leaving you to do. What you will do is you will do del f1 by del c. You will determine del f1 by del t. Similarly, you will determine del f2 by del c, and you will determine del f2 by del t. All you need to do is you need to write equations corresponding to function 1 and the functions corresponding to function f1 and f2 as functions of c and t. So, r would be converted to k 0 e to the power minus e upon r t, c already is there, and then you differentiate, you do partial differentiation with respect to c and t. When you do this, you can write a Jacobian matrix. The Jacobian would be del f1 by del c, del f2 by del c, by del f1 by del t, del f2 by del c, del f2 by del t. Okay. And then you will determine these, if you remember the procedure, you will determine these Jacobian matrices at steady states. So, steady state, let me write it explicitly, at, you will determine this at t steady state t is with 3 1, this is the notation we used, right, T s 3 1. You will determine this as at j t 3 2 and j t 3 3, right. This will be the first step. Then you will determine the eigenvalues. You will determine the eigenvalues. It is a 2 by 2 system. So, there would be 2 eigenvalues. When you plug in all the values of say the heat transfer coefficient and density, flow rates and so on. When you do this, then you will realize that these 3 points which you obtain, this point 1, point 2 and point 3 have different stabilities. Okay. So, you will find after doing this analysis that the middle point T steady state 3 2 is unstable. This point is stable and this point is also stable. You will get this. Let me repeat what you are going to do. You will take functions f1 and function f2. You will do the partial derivative. You will determine del f1 by del c, del f1 by del t, del f2 by del c, del f2 by del t, from where you will get the Jacobian. The Jacobian will be determined at these 3 steady state temperatures. When you determine the Jacobians, expressions for Jacobians, in fact the components for the Jacobian at these 3 points, you will be in a position to determine the corresponding eigenvalues. These eigenvalues will always be such that the middle point is unstable, which means that both the eigenvalues would be positive. That is the nature we saw previously, and the first and the last points would be stable, which means that the eigenvalues would either both be negative, or if they are complex numbers, then the real part would be less than 0, the real part would be negative. Okay. We saw that in both the cases the system is stable. One case would be sink solution, the other case would be a spiral sink solution, right. So, therefore, when I have this in this particular diagram in front of me, let me draw this diagram again and do a further analysis. So, this is jacket temperature versus steady state temperature. The system looks like this. So, I have now this particular bound to my system, okay, and this portion will not be observed, because this is you will do it for a large number of different parameters, and this portion is unstable. You take any of the vertical lines in this portion, you will not get any stable solution. So, therefore, you will not observe the system. So, if you start your system vertically in this proximity, if you are away from this particular line, you will come to that line, come to that point. Similarly, vertically, if you start in the proximity of this point, you will end up at that point at the steady state. But now I am now keeping on decreasing the temperature, my jacket temperature. Okay. Now, if I keep on decreasing my jacket temperature, what I see is that I no more am on that particular stable point, because now I am in this unstable region and I come down to this point. I come down to this point. Similarly, if I start from temperature, lower temperature and go, you end up here. So, this process of going up, is called ignition, because now you are not able to control your temperature, the temperature is automatically going up because you are in the unstable region. So, this process is called ignition, and this process of coming down is called extinction. So, you see an ignition extinction behavior in case of this adiabatic operation. And then this was a particular case when you took the x axis or you did the analysis with jacket temperature. You can draw this curve for feed temperature as well. The nature of this curve would be same. Hysteresis is what you would observe there as well. You can take this x axis as the space time, again you will see a very similar behavior, that you will see a hysteresis, you will see ignition and extinction behavior in your system. Okay. And then what you will see is that this seemingly very simple system, which is a CSTR, you are stirring it, you are sending it a jacket fluid, and a very simple reaction A going to B, not reversible, simply irreversible reaction, not very complex kinetics, first order kinetics, KCA, gives to this exotic behavior in the dynamics of your system. So, what we saw today is that when you have nonlinear dynamics, when you have a CSTR which is operating under diabatic condition, you may experience dynamics which would be non-intuitive. Intuitively, you may feel that if I start with one set of parameters of my system and I maintain a steady state, then I should get a unique steady state temperature in my system. That in fact does not that in fact may not happen. I should not say does not happen, that may in fact may not happen, because your system is highly nonlinear. And what is the reason behind this observation of non-unique steady states? The key reason behind this is that you have a you have an energy removal curve in your system which is non-linear. Sorry, not removal, generation curve. You have a heat generation curve in your system which is non-linear. Your heat removal curve was linear, your heat generation curve was non-linear. So, there was a possibility of intersection of these two curves, one linear, one non-linear, at multiple points. In fact, if you remember our previous discussion, you have saddle node or tangent bifurcation in your system, in which you can have the intersection at just one point, you can have intersection at 2 points, and in this particular case you can have intersection at 3 points. And because you have multiple intersections, you have multiple steady states. So, now it is important to determine whether the steady states which you observed are stable or unstable. That can be done with the help of linearization. Why are you assured that this linearization would work? If you go back to our theory, you will find that the solutions are hyperbolic, which means none of the eigenvalues are actually 0. So, therefore, you get 3 in certain cases you will get 3 eigenvalues. One of the eigenvalues in one case, both of the eigenvalues would be greater than 0, they would be positive. So, and that would happen for the middle steady state. So, your system would move away from that, that would be the unstable steady state. The other two steady states would be stable. They can be sinc solutions, which means both the eigenvalues would be negative. They can be spiral sinc solutions, which means that with oscillations you will settle down to that particular steady state solution. So, we will stop here today. We saw how interesting nonlinear dynamics of reactors are. We will take 2 more examples of nonlinear dynamics in the week to come. Till then, goodbye.